Okay, thank you. First of all, I would like to thank the organizers for giving me the opportunity to talk about this subject, and I changed the title a little bit in the spirit of this conference. Now, electrolytes, of course, well known. The DNA is maybe the best studied case, but you have glycosaminoglycans as, for instance, heparin. So these electrolytes are just everywhere, involved in most biological processes. And in particular, the complex formation of electrolytes with proteins is a very important subject. Let me just flash up the glycosaminoglycans. So you have sugar repeating units with 3 sulfur groups and 1 carboxyl groups, and then you go down in charge. And so this is obviously very important. So nature is using different charges and charge densities. And of course, the question is not only ion-specific interaction, but it's a role of water, which we always have to consider. And since Christos is in the audience, I should show a dendritic structure with charge N groups. This has been done by Rainer Haag, and you can use this charged dendrimer as a drug. It's an interesting thing, and you can replace heparin, for instance. So it's very interesting to use these synthetic electrolytes as drugs as well. Now, it's not only charge-charge interaction. If we talk about electrolytes in biology, we are pretty soon ending up in the famous or infamous Hofmeister-effects. So if you look into the extracellular matrix, you have sodium chloride mainly. If you go to certain bacterial cells under stress, you have potassium glutamate, for instance. So this is an interesting effect, and this is very much related to the hydration. So we have to understand this in great detail and model it. So let me just give you a quick menu. I would like to talk about thermodynamics. So it's no statistical mechanics, it's just phenomenological thermodynamics. And I would like to show you one application of this approach. Now, this is, as I said, one of the most important problems. You have DNA interacting with some protein. We know a lot about these structures from crystal structure, but in solution, of course, you don't have a structure anymore. And I think a very important point I would like to discuss with you today is you have a certain release. So you have this chemical reaction, electrolyte plus protein, gives the complex, which is shown here. But then at the same time, you release quite a number of counterions and water molecules. So it's important to recognize that you may release up to 2,000 water molecules if you form a complex from DNA and a polymerase like Glentag or so. So if you release 2,000 water molecules, the question is really, is maybe the release of water the decisive effect? And there are people in the literature who claim that this is really important. However, if you just have maybe a tenth of kT, then you would shift this to the right side by 200 kT. That's impossible. So Mother Nature must find a way how to deal with this huge release or uptake of water, depending in which direction you go. And I think it's quite good if you look into such a chemical reaction to go to early approaches, which has been done by Jeffrey Wyman already in the 60s of the last century by the so-called linkage relation. So this is a precise, exact thermodynamic relation. You differentiate the free energy with regard to the log of the activity, and then you find the number of released counterions or the water molecules. Now, Tenford in '69 already discussed that this is, of course, not a meaningful operation, because you have a dilute solution of your protein and DNA. So in essence, it's a dicomponent system from water and salt, and by virtue of this Gibbs-Duhem relation, you fixed the activity of water by the activity of the salt ions. So if you go along these lines, then you can write down the correct equation. Namely, you look after the change of the binding constant with salt concentration, you get two factors or two terms. First of all, you get the number of released counterions, and this is the hydration parameter. So we have two terms which may be important, and we have to go along these lines in more detail. But first of all, you find out that the activity of the added salt is a decisive parameter. And we will see later on, we saw already in many talks here, that salt sort of replaces temperature in many phase diagrams. Now, if you go along these lines, you can show that this term here leads to a term which scales with logarithm of the salt concentration. If you go to the hydration term, you can show that this scales linearly with salt concentration. Now, then you can convince yourself that this first term will dominate at low salt concentrations and this one at high salt concentrations. So if you go along these lines in a total model-free fashion, this is, I think, very important. There are no further assumption necessary. You have not only the salt concentration as a decisive variable. If you change salt from low concentration, say 20 millimolar or so, maybe to 0.3 millimolar, 300 millimolar, then you can get the two terms separated from each other. And this is kind of nice. And again, as I said, no model is necessary for this kind of exercise. Now, let me first of all come to the number of released counterions, and we already talked about counterions on condensation. And here I found it very expedient to use the age-old Manning theory. So you have a certain number of counterions, and you can easily estimate the number of condensed counterions by this charge parameter. And if you are not working at very high salt concentrations, the added salt does not change the number of condensed counterions. This is a little bit of a difficult point, and this has been challenged by many workers in the field. But if you go through the early work by Alexandrovitz and Kachalski on osmotic coefficient, and I strongly recommend, this is a very clean work and experimental work, and it has been used already by Manning. And there is a very nice and very comprehensive simulation by Magnus Ullner, and Netz and others were already working on this. So it's a good assumption, and you will see later on this is very useful. So if we now have condensed and free counterions, so we have a certain surface concentrations, a high concentration here of approximately of 1 molar salt solution concentration for the case of DNA. Then we can look into the free energy into this logarithmic term, depending on salt concentration and some residual term. And you can approximate this term by the number of that. This is the number of charges involved in the binding. And then you have this 1/2, the Manning parameters. If the Manning parameter is large, then you have delta NCI is practically that. So this is a very simple prediction which you can compare to experiments. And then also we, to illustrate this model, we said, okay, let's take the protein, and we have a patchy surface. We discussed this at the meeting already several times. Here you have the condensed counterions. You form the complex, and then you release a certain number of counterions and you increase entropy. And you will see in a minute, of course, entropy wins the game. So we were quite confident, good model, and it's age-old. I should say this model is going back to people like Thomas Reckitt, to the 70s of the last century. It's really not a new thing. But as science is, and this makes us life interesting, suddenly someone shows up and say, no, forget it. It's nonsense. And this was Chenggang Wang in 23. He said, well, this is not counterion release. It's the reorganization of the water dipoles. And this is, of course, a very famous demonstration. You have two ions in water, and you have a strong ordering of the water dipoles by the monopole interaction. You make a pair, and then you have, of course, only a dipole, and the strong ordering of the water dipoles is relaxing. So that's it. It's not counterion. Chenggang Wang did, I think, a very good thing. He looked into the simulations of Muthu Kumar and co-workers. So Muthu Kumar in 2006 did a lot of simulation, and then you calculate from this energy the partition function and so on and so forth. But if you want to calculate entropy, you have to take the first derivative with regard to temperature, and then you are in troubles because the energy here is itself a function of temperature through the dielectric constant. So we have to have take an additional term. So if you do it, you don't get the classical equation that T times delta S is minus F and plus E, but you have some correction term of appreciable magnitude. And so you have to correct the simulations. When you want to calculate S and, of course, the enthalpy, you have to correct these simulations of Muthu Kumar. I guess Professor Muthu Kumar was not very pleased when he saw the paper coming up in the proceedings of the National Academy of Science, but of course, Wang is right. So this is very clear. Now, we were quite concerned, so I teamed up with my colleague Roland Netz, who is an extremely smart fellow. So we looked into the most simplistic model you can have in electrostatics, namely the Guy-Chapman model. You have a single charged plate, you have the counterions, and you have two parameters, namely the so-called Guy-Chapman length. Half of the ions are here within the distance of the Guy-Chapman length, and of course you have the usual Debye length. And if the Debye length is much larger than the Guy-Chapman length, you have a highly charged plate. And then you do a simple exercise. You have a very small probe charge, and you look then into the reduced surface potential, and you can connect this directly to the free energy. And then you can, of course, do two calculations. You calculate the free energy and the first derivative, the entropy. When you simply take epsilon, the dielectric constant, as 80, and you leave it there, or you plug in the experimental value. So you have two curves here. This is the free, the different bits of the free energy, of course, remains the same. Here you have the entropy, and we did two calculations. One with epsilon of T, which you can get from some tabulated values, and then we took it as a constant. So you see that at highly charged systems, and this is, of course, the most interesting system we look into, we have only approximately 1 kT difference, not a big difference. However, if we go to lowly charged systems, so the Debye length is of the order of the Guy-Chapman length, then you see big differences. So the solid lines are the calculation for the correct calculation, and this is a wrong calculation. You see big differences. This is exactly what Wang et al. Saw. So from this, we calculated or concluded that there's not a big difference But it taught me again, I've been teaching thermodynamics for quite some time, but again, you discover something new because the free energy is delta H plus its first derivative times T. So if you want to get some information about entropy, change the temperature in your experiments as well. Then, of course, we looked into two parallel plates. We want to study the counterion release. And then this is in particular the work of Safran. It's very important. And so you have two plates of equal size, opposite charge, and you calculate their interaction. And then you indeed see if the distance between these two plates is smaller than the pi length, the counterion release starts. And for typical biological systems, this is approximately 1 nanometer. This is a long distance. So the attractive interaction starts already far apart when these plates do not touch. In the final state, you have, of course, you have some interaction there too, but the main attractive force is the counterion release. And you can show this numerically. This has been done by other people as well. So I think if you have highly charged system, counterion release can be shown by this type of argument to be the decisive variable. So now let me come to the problem of water. We have to resolve this at the same time. So this is a rough cartoon. So you have a hydrated water around the protein. You make a close contact with the polyelectrolyte and you release water, and a lot of water, depending on the size. And then I learned a lot from the solid partitioning model, which I think is quite a good theory for Hofmeister-effects. So what you do is you look into the preferential solvation of salt ions, for instance, in the local domain in the hydrate shell, and you compare it with the bulk solution. And then you can calculate this in terms of a partitioning coefficient, which is, for instance, small for cosmotropic ions. So the cosmotropic ions do not penetrate into this hydration shell. If you are in the middle of the Hofmeister series, typically sodium chloride, something like this, it's a unity. And if you then calculate from this model this parameter, the second parameter, then you see that if Kp plus minus is approximately unity, then you can try to release as many water molecules. This decisive hydration parameter is 0. So you release a lot of water molecule, but the decisive parameter for the free energy is very small. And this comes out very nicely from this solid partitioning model. Now, we did, of course, a lot of experimental studies with isothermal hydration calorimetry. I should note in passing that this is a difficult problem because ITC needs a bucket full of material. If you tell your friends from biochemistry, I need 100 milligrams of some protein, they are nearby killing you. So, but you can use this, and this has been used, of course. And I really like the study by Likeda and others 20 years ago on Clentag DNA. So this is a big protein, the polymerase Clentag, interacting with DNA. And here this is the ITC data. And you have this particularly slightly skewed parabola shape. And here you have, if you look into the salt dependence, you have approximately a straight line. And you can split up this into this counterion release term and some hydration term, which is temperature dependent. There's another point overlooked by many workers in the field. This is very general. So if you look into the change of free energy here, or ln of the constant, you find that this is very flat. So the temperature dependence is very small. And here it's even 0 at a temperature Ts. So here is the entropy is 0, here Th, the enthalpy is 0. So these temperatures are close by, and this means if you have here delta H, they scale with delta S scales with the delta Cp, of course, and T delta S in first approximation to, then you have a strong variation of H and S here, but a strong compensation in first order. You find that if you have these two relations, that delta G is even a constant. And this is a famous entropy-enthalpy compensation. And that's very typical for these biological systems because delta Cp is a large number. Delta Cp is far bigger than entropy and more important. So this is another point. If you do simulations and smart theory, don't forget delta Cp, which is decisive. And if you now do the calculation with this simple model, you find out that the same thing. You have delta G is practically constant. And then I believe that the main point here is that you release or take up water. And for each released water molecule, you have to bring in enthalpy, but you gain entropy. Or you put in water, you gain enthalpy, but you lose entropy. And this is nearly canceling out, as I showed earlier, by this hydration parameter. And this is the way how Mother Nature handles water. And by the way, personally, I believe this is a reason why many water-free simulations work quite well. So water sort of cancels out to a certain extent. Now we did a lot of studies and looked here. So we have this small dependence, this parabolic shape, and so on and so forth. And I think the most interesting point is that if you go ahead and you take the same lysozyme and heparin and let them interact in one experiment with sodium chloride, and then you go off to the, I think, left side of the Hofmeister side, Hofmeister series, you put in potassium glutamate, then you see that this first derivative, the second derivative of this curve is changing. The overall strength of the interaction is comparable, but the temperature dependence is changing drastically. And you see here, so one can go into the details. And one more important point, if you go to low salt concentration, as I told you, it's electrostatics dominating. The electrostatics is independent of iron. But if you go to higher concentration, then you see drastic differences because of these iron-specific effects. So you can take this apart. Okay, now we have hopefully learned something about it. Can we do something with this? And of course, yes, we can. And this diagram has already been shown this morning. So I think these biocondensates are sort of a revolution, not in biochemistry, but in biology in general. So there's a lot of things which we have to understand. And I found the particular experiments by Matt Tyrrell and co-workers very well. I think Matt was the first one to show really that you have this classical or simply classical looking phase diagram. But now, instead of temperature in the Fleury-Huggins textbook type, you have salt concentration. I think from what I said, it's very clear. You have two decisive variables, namely temperature and salt concentration. And so I was lucky to meet Ben Schuler, who did a very nice study on biocondensates by two model systems, which I should bring here. So normally you do ITC experiment, but then you cannot stop the complexation at this binary stage. However, if you do fluorescence spectroscopy as done by Ben Schuler, you can go to very low concentrations. So you can stop the reaction at this stage and analyze it separately. Then you get the full thermodynamic data from the experimental binding constants. So here we go. So we first have this first prothymosin alpha plus this histone. They form this binary complexation. You have the binary complex constant, and this is the free energy. And then you go to higher complexes, and you can sort of take apart the full complex formation and the phase separation in this way. And this is and here I just wanted to show you the step 1 analysis, the step here. So just binary complex formation. And yesterday we were talking about the grammar of such protein sequences. And it's very evident that prothymosin alpha, the anionic material, has this blocky structure. And this is no mystery. You can again invoke good old Manning, and you see that you have here the charge parameter far above 1 here as well. So you have here a strong ion condensation along on parts of this prothymosin alpha. Now let's go to the cationic system, this histone. And then you see a totally different structure. You have always these lysines interrupted by other amino acids. So this is a totally different and non-blocky structure. And if you go along this, you know this is the so-called Cardin-Weintraub sequences, and you find indeed this is a totally different thing. Now, to wrap up the story, you need just 2 diagrams. You need the salt dependence. These lines are approximately parallel. They tell you counterion condensation is the important, or counterion release is important. And you have the salt, the temperature dependence. And what you find here is delta Cp is negative, and the strong negative enthalpic contribution, which brings about binding, is balanced by strong enthalpic contribution. Okay, let me just show you the data, the conclusion. So the analysis, I think, can be done in a purely thermodynamic fashion. And I should stress that delta Cp may be, under certain circumstances, a more important parameter than delta S. And my personal conviction is you can understand even complex biochemical processes in terms of analytical models. It's not impenetrable biochemistry. Maybe the biologists would think about this differently. Yeah, let me thank the people who were involved in this work. And I'm particularly thankful to Ben Schuler and Cheng Yang Wang for having discussions. And I thank you for your kind attention.